Hello, this is Prahashdeep Singh, and I will be giving a demo on how a PPG sensor works. So basically, we would be given a data, which would be the heart rate or the readings of the heart rate obtained by converting the analog signal to the digital one, digital analog heart rate to the digital signal through a sensor. We were given this signal in this experiment. This signal is defined by array 150. We are defining some global variables for this code. The global variables are L, which will be the window size of our moving average filter, and the data size, which is the data size of this array, of the given array, and a random variable means float variable. It would can be used in the mm, in the in the blocks to calculate and evaluate the signal. So first we start. So basically this experiment consists of many parts. These parts can be modulated as uh, first we uh, we pass the signal through a moving average filter, move f AF. Then we pass the signal to the first order derivative filter. Then we pass the signal to the moving average filter, and we check the peaks, and then we get the distance, which basically is the distance of our pulses, which gives us the pulse rate. So now moving on. So first we initialize all the contents of this array y150 y, or the contents of y1, which have 150 contents, to be equal to all 0. So basically int I equal to 0. We start with the counter I equal to 0, which 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 extends up to 150, which is our data size, and by each step I is incremented by 1. So now we will now we'll analyze each of the working of each of the blocks in detail in below code. So void setup is the Arduino based uh, block, which basically tells Arduino to run this code once. Void loop runs the code in a loop multiple times. It runs for infinite number of times. Serial begin 9600 gives us the baud rate, which is the number of bits transmitted to the Arduino and received received to the computer or processor. Void first let's start with the display. How are we displaying our signal? So like I uh, let me first negate the effect of all the filters or the code. So we would be just plotting the signal. So I will be commenting the filter blocks. The filter blocks or the working in the uh, blocks gives the dynamic programming in edge, and through this we are able to utilize the memory efficiently, as the memory size of our Arduino is very limited. So now I'm going to run the display loop to observe our original signal. So I'm going to upload the code. So it's done uploading. Now I'm going to plot the signal. So we can see that basically the signal has some peaks, and we are interested. Let me open it once again. I've saved it. So basically our signal has some peaks. These are the peaks, and we want to calculate this distance accurately, so that we are able to measure our heart rate or pulse rate. So now moving on to the code. So mm now we want move on to the display block of the code. So basically it has two input variables, which are ARR and Y. which are taken from the our ARR is our original signal, original given signal, and y we will compute, or the assessed version of the original signal or analyzed version. We can also call y as the we would perform some operations on ARR array, and then we will obtain y, and we will plot these signals simultaneously to observe what's the difference between the two. So let's proceed. We observed the original signal. Now we'll pass the signal to the moving average filter. So moving average filter, this is the code. This is the code for moving average filter, which would be given here. So the moving average filter takes two inputs. One is the see one is the array itself, this array, which has 150 elements each, 150 elements, and L is the window size of our moving average filter, which will be which is a global variable and is defined at the top. So now moving on the moving average filter. So basically we want so basically we can now see how a moving average filter works. So for int I, we will define an I, which is a counter int I. Now for I equal to 0, less than data size, which is 150, and I plus 1, we will increase it by 1. So now we want to calculate. So if say if L value is 3, so these this whole array of, say this is array, this is our given array, and we want to obtain this array. This is after we have performed the operation of moving average filter. So now for I equal to 0, this will so through this code up till this start over here and end still here. So up till this loop, we want what we want to do is we if L equal to 3, or up till the counter reaches L, we want to take the average of those bits in the new created array. So this element would be here, and average of these two will be here, average of these three will be here. Then after that, when L equal to 3, if our L would have been equal to 3, then after that, for this equation, it would always calculate the average of 3 and place it to the bottom array. So if here it will calculate the average of these three past values and the present values and place it here, and here it calculates the average of these values and place it here. So for doing that, what we have used is, if I minus L is less than 0, basically for if the counter is less than 3, and while we have defined a new variable j, and j would be defined as 0 as I equal to 0, first this condition would always be true for the first I equal to 0, and then in j would be initialized to 0, and then so I minus j would be always greater than minus 1 initially, and then basically this is the adding of these two elements. If j is less than I, and then basically we would be taking the average of these three or these two, and if these two, then placing it in, dividing by j and placing in this element, divide by 3 and placing in this element. If for this experiment our L is 5, so we'll be proceeding as we'll be placing this element here as it is, dividing this two element, adding these elements and dividing it by 2 and placing it here, adding these three elements and dividing it by 3 and placing here. So this sums it up till here. This is the case as I minus L is less than 0. This condition is satisfied as after each placement j is incremented by 1, and the final result is divided by j. Now we can move on the later cases where we have the counter has proceeded the initial L value, and we observe that through this equation I y I equal to y I minus 1 plus array 1 is the new array which we defined new array. It's the array 1 would be the new array. So uh, array 1 array 1 we captured. Array 1 is the array on moving average filter which we captured from moving average filter, and this is the given array. And yi is the array which would be modified, which is yi is the global variable which would be modified for the whole of the code for the further proceeding for the further processing for the further signal processing. Now moving on to this code, this line. So basically we are taking the average of the elements up till L and dividing it by the L. So basically we are averaging. So after say this element, if L equal to 3, we'll be averaging, we're taking these 3 elements and averaging it over here. So moving on to our code. Now we have now after performing the moving average filter operation, on our initial code, we can observe that our signal will look something like this. So this is our original signal, and after performing on operation of moving average filter, our signal will look like this, which will have remove which after, as we can observe from this signal, we are able to remove the high frequency components of noise from this signal. Now moving forward, so now I'll be explaining about the first order derivative function, which is given over here. So in this function, um, we are taking the input as y. So this is our input. Let's observe here. This is y. So basically, the new changed array, this this would be our changed array, and on this array our next signal processing would be performed. Further signal processing would be performed on this array. So now we would be we'd be taking the first order derivative of that function. So basically first order derivative can be for digital domain can be defined as the difference elements, which can be given by yi equal to y my I minus y I minus I my I component minus ith element minus I minus 1th element. So now moving forward, say uh, so now I will explain the first order derivative function. So this in this experiment, in this block, I'm storing the y derivative function as a new variable which will store all the values of yi at first. So so like if this is our yi, then we will first replicate y derivative of I to be exactly like y of I, and then for calculating the y of I, we, uh, we will we will say this is our y of I, and this is our new yt of I. Then we will first duplicate this. Now these two arrays have the same element. Now we will calculate the difference of elements, this minus this, and put it here, this minus this and put it here, this minus this and put it here. So yt minus yt of I minus yt I minus 1 calculates the difference, and y of I equal to this equation just puts this to the difference in the above array. And this is the copying expression, and this is for the placement of the variable of placement of the elements in the yth element for which on which we have performed the signal processing of derivative. Now we can observe the derivative signals the obtained now we can observe the signals obtained after we perform the derivative operation. So as we can see in this signal, This is the signal obtained after we perform the derivative block, after we uh, after we after we compile the so this that that was the output after we get after we compile the compile and plot the derivative of the function. So now moving forward, uh, now we have done the now we have done the derivative first order derivative operation. Now we will calculate the moving average filter operation once again over data over the first order derivative operation, so that we were able to further reduce the noise, high frequency noise. This can be visible from this graph. See the how the high frequency noises are removed, and also we can see uh, that we are able to calculate the derivative of the above of the blue function over in the red function or graph. So now I'll be moving to the next part of the code, and that is to calculate to detect where the peak happens. So which I named as peak detect. So here's the peak detect part of the code. So here we are first we are first we define in count function I, and I equal to 0 up till 150, and then when we to calculate the peak detect, first we take all the values of yi. If yi if less than equal to 0, then we put y of y equal to 0. So basically all negative values would be summed to 0. So sum no, would be taken as 0. Now moving on, in flag equal to 0 would be our flag counter, and sum equal to 0 would be our sum counter. This would be useful when we would be calculating the threshold value. Now moving on, for int I equal to this, this is basic definition of the to observe the maxima y, which says that y ith element is greater than both the I minus 1th element and I plus 1th element. And also I have used this y of I is greater than 0.001 to negate the effect of the small maximas, that small maximas or irregular maximas that will come. Now we as we move on now, uh, else so here we will just take if yi is if y if this it is greater than 0, then we will put it as yi, else we will put it to 0, and then we will calculate the threshold at sum equal to sum by flag, where sum is uh, the the peak value. So here the sum is sum is counted for each peak, the amplitude of each peak, and flag is the number of peaks. So we will calculate the threshold as sum of all the peak values and divide by the number of the times the peak occurs, and then by we will set the yi equal to 10 times of yi, so as to detect the peak more accurately. Here in this graph, this is the peak, these are all the peaks that we get. Now moving on, I would be calculating the distance. So distance between two values of the peak would be calculated as, in this code what I'm trying to say is, uh, um, the for each element, if for each element first I'll get this element, say I'll get this peak, and then the next time this peak occurs, the yi value would be changed from 0 to some other value. So I would be able to identify the ith element between and for which we are getting the peaks. So now moving on towards the code. So this is the distance part. So these are the flag and distance. Distance is the difference between the elements for which we are getting the peaks. So here we have done for int I, once again we run the code for 150 elements, and if yi is greater than 0, we start the element, we start our counter, and it will move up till yi is again greater than 0, and then we will increase our flag. So basically distance would be I minus the start value. So if we are moving with I, some I, some I, some I, some I will come, and then this I would be greater than 0, so our start would be set at here. Then each time start would be incremented as I would be incremented, I increasing up till here. Then as this comes greater than 0, our start would again be set to 0, and distance will be calculated as this distance. So so this is that code. And now to calculate the beats, as we are taking a signal of 50 hertz, so this is our signal, distance equal to distance divided by 50. This is our effective signal, and in beats per second. So this would give us beats per second. Now to calculate the beats per minute, beats per minute, we multiplied by the signal by 60. So now I'll be running the whole of the code to monitor what's going on. So let me remove these comments. Now we will upload the code. So now we'll observe the values in serial monitor. So okay, let me see once. So we will comment this section, as we don't want our values to run to infinite. So we are able to get what the beat rate is. So as we are getting 73.8 as the distance, so this is the beat rate. 3 is the number of peaks, and 123 is the distance, the ith element distance. So here I conclude my demo. Thank you.